Good evening, ladies and gentlemen. My name is Eglinton, Geoffrey Eglinton. I'm one of the retired professors here. I've been brought out of retirement to be given the great pleasure of introducing tonight's speaker. I'm actually a retired chemist, although I metamorphosed into what's known as a biogeochemist. So I think I have some entitlement to introduce the speaker, because Gerald Haug is a distinguished climate geologist, and he's in this institute in Switzerland at Zurich called the ETH or ETH. I won't attempt to pronounce the thing because Gerald thought it was inadvisable, but it's a very distinguished place, the equivalent of MIT, I would say, in many ways. Gerald is going to talk to us about the connection between the geology, the marine side of things, and climate change and that of society as a whole. So, how is it that I should be introducing him? Well, it turns out, of course, that there are all sorts of hidden reasons. The first, it is not the first time that Gerald has come to Bristol, because back about 10 years ago, he came here to work with me and colleagues in the Biogeochemistry Centre, which is in this very building, to work with some methods that we had devised to measure, of all things, the sea surface temperatures of past oceans. You may think that's a pretty difficult thing to do. Well, you can't actually measure it, but you can estimate it using molecular tools. And we had devised such a tool, and Gerald came to use it. Now, how did this come about? Well, it's really a strange story, because it all began years ago when I was attending a small conference in 1980, and I found I was sharing a room with somebody called Michael Sarntine. Now, Michael Sarntine, it turned out, was a sedimentary geologist, and at that time I was more or less a so-called, inverted commas, pure chemist. So we found that the room temperature in the Barbados was rather hot and humid. And we tried to get to sleep, but we couldn't. So we started to talk. And we spent most of the night, actually, me telling him about chemical things and he telling me about geological and climate things. Well, we then decided that it should be possible to collaborate to try and put together the chemistry and the geology to tackle an area in between them, which was to do with the ocean sediments. So, over the years, the group in Kiel in Germany and ours here in Bristol collaborated, and we came up with a new method of looking at these ocean temperatures, which we called UK 37 in a somewhat nationalistic way. And this proxy, as we called it, was presented as a joint thing from Kiel and Bristol at a conference in Germany. Well, things went on for quite a little while we developed this, but then in 1994, I think, was Gerald, is that right? Gerald suddenly appeared on the doorstep here in Bristol, and with something like 1,000 samples of sediment from the Pacific Ocean, and said he wanted to measure these sea surface temperatures. So that's what we set out to do, or at least he set out to do. And 6 months later, he'd accomplished this. But the wiggles, as we call them, the temperature profile along through time that he constructed, looked really very strange. And he disappeared back to Kiel muttering to himself that it seemed to be very strange and difficult to interpret. Well, that was that for quite a while. But then, all of a sudden, in 2004, I think, a message came from Gerald to us saying, I think I've solved it. And what he'd done was to correlate these ocean temperatures that he'd estimated with the climatic history of about 2.7 million years ago. And what seemed to be the suggestion he was coming up with was that the warm water in the Pacific, which was unusually warm for various reasons, was giving a lot of moisture to the atmosphere, and this moisture was being dropped on the North American continent as ice. And this was the start of the Ice Age, 2.7 million years, the whole process of cooling like that. So it's a strange combination. Warm water, increased temperature, and more ice. But then this actually makes a lot of sense when you think about it. And so tonight he's going to tell us more about this sort of thinking of connecting the geology to climate, and then from there on to what the effect is or can be on human civilization. Thank you. Gerald.
Well, Jeff, thanks for the very kind introduction. Ladies and gentlemen, good evening. It's a real pleasure to be back here in Bristol. It's exactly 20 years ago when I came first. It was 93 in September. And indeed, we stole 1,000 samples. Everybody thought, this guy is kidding, it can't work. And then when I left, indeed, I had this measurements done, and you will see some of this in the presentation. The onset of Northern Hemisphere glaciation is one of the most unique events in the entire Earth's history. We have ice sheets only since 2.7 million years on this planet, ever of the last 550 million years ago. And what I found, based on those temperatures, when the world would plummet into an ice age and everything got colder, I found in the North Pacific a 7-degree warming. And that was not a good idea. So I came back to my advisor in Kiel. I said, well, young man, you wasted a fair amount of my research money and 6 months of your time. And all I can say is stupid. And then it took 12 years to publish this, which is also not recommended for a young scientist, but still worked out. Anyway, what my co-authors and I want to do is to give you a short introduction on the impact of climate on past societies, but in particular bring the huge experiment we are doing with our atmosphere as today's society on climate into a geological perspective. So this is a scientific presentation. I expect everyone in the audience to have a PhD in physics as a minimum requirement, or in geology would work too, but I still try to do my best to make this well understandable. So I have 6 topics here. First, I want to very briefly review the human impact on the carbon cycle. And then to start with the geological perspective, where we really know what CO2, and that's the key impact of the carbon cycle, are changes in the atmospheric concentration of the greenhouse gas CO2, is the glacial interglacial timescale, when ice cores give us very precise measurements of the last 800,000 years ago. The reason for being here, and it's just a wonderful endeavor, is this workshop on the Pliocene warm interval. So 80 scientists from worldwide gather here at Bristol to look at the so-called Pliocene warm interval. That's the youngest geologic analog where the atmosphere, as we just approached, it was just above 400 ppm. This is where we have to go back 5 million years to review the last geologic analog of a real warmer world. But this may be not good enough. The world cooled since 50 million years ago. So at the moment, it looks like that the human experiment is overshooting CO2 so dramatically that we may have to go back this entire 50 million years ago to get the full amplitude on what we possibly do in a century or two. And then for those in the audience, if you still have breath, we go to make a huge jump in time scale back to the last 5,000 years and look on the decadal time scale of the impact of climate, in particular the tropical climate. Much of climate change is not about the temperature change, it's about the hydrological cycle and why we really need to care, in particular also in the combination temperature and hydrology in the planet. And then that we to make sure we're not getting too depressed. What can we do? We can do a lot is the message. We're not doing it at the moment. So what we do at the moment is portrayed here. This is the time scale 1850 to today, towards the end of the century, to 2100. And this is the CO2 emissions in gigatons or petagrams carbon per year. So we've increased by burning fossil fuels the CO2 emissions, and these are the different projections given by the IPCC, the World Intergovernmental Panel of Climate Change, and these are the different scenarios based on business as usual to some mitigation scenarios, what is possible. And I try to make the case, and I think it's probably true for all those colleagues here in the audience and most of those who work professionally on climate change, that it would be a very good idea to reduce the burning of fossil fuels and stabilize the atmosphere at 450 ppm. That's still above what we had in this Pliocene warm interval. Unfortunately, at the moment, these are the measurements here. This is the detail, 2012. We've just passed 9 gigatons of carbon per year. We are on this extrapolation. So we are really shooting up. We're making probably an experiment which this planet has not seen in the entire Earth's history. Right? That rate of change is unparalleled. And we are, despite all the talk, probably going to miss destabilization. And it's quite open on how much more of fooling we will do with our atmosphere. CO2 is a greenhouse gas. I don't need to explain this any further. The potential extrapolation on the global warming based on these emissions ranges based on the different scenarios by the end of the century between just about below 2 degrees Celsius and up to 6 degrees Celsius. So this Pliocene warm interval, this conference is all about, is a world which is 2 to 3 degrees warmer than today, had as a maximum CO2, atmospheric CO2 content, something like 400 to 420, 430 ppm. So this is why we as geoscientists believe it would be very good to stay within this EUC policy limit below 2 degrees Celsius, which absolutely requires a stabilization at 450 ppm if we don't want to go to the Pliocene warm interval. And the Pliocene warm interval was just the time before Northern Hemisphere glaciation started. And there was an ice age, and like today, a warm age, which still had an ice sheet on Greenland. So that's an ice-free Northern Hemisphere, and we already know, and I'm going to explain this further later, that this would mean a sea level rise of 6 to 7 meters if we get rid of Greenland, and the Western Arctic isn't that stable either. We often confuse climate with weather. Do we feel this climate change already? I mean, there's this confusion, but I think they're very strong indicators depending on where we look at. The strongest impact on the so far 0.9, close to 1 degree Celsius global warming is seen in the polar oceans or the poles. You see here the evolution of the sea ice, the summer sea ice in the Arctic Ocean. This is the extrapolation from the model results here. This is 1950 to 2050. Here would be the 2100 of the model projections from the IPCC4 report, and it looks like the actual measurements are actually pointing out that the models, the IPCC, is a probably too conservative approach and is underestimating the sea ice melting, which depending on the scenarios may disappear as early as mid, probably late this century. You see here a map of the Arctic Ocean. This was the sea ice minimum in 27, and it's decreasing quite rapidly. There's also on Greenland a strong reduction or increase of the melt area, which is this trend. So there's no doubt about that the globe is warming, the climate is warming based on greenhouse gas emissions. So here is the increase in atmospheric carbon dioxide of the last 1,000 years. This is 1,000 before present, this is today. These are measurements from the ice cores, and then these are the measurements from in situ on the Mauna Loa, Hawaii Observatory. So we've just pretty much reached 400 ppm CO2. We are just below 400 ppm once we just hit the mark. And these are the numbers from the, in a month, upcoming IPCC 5 report. The fossil fuels are the clear main responsible as the burning fossil fuels. We've introduced so far anthropogenically 365 gigatons of carbon to the atmosphere. The land use impact, deforestation in particular, is 180 gigatons, so the total emissions are 455 petagrams. Those who make the calculation quickly, that number doesn't work with the about 2.13 ppm increase in atmospheric CO2. And the reason for this is that at the moment, the natural carbon cycle is helping us tremendously to take up all those man-made emissions. It's about half, which the ocean is taking up in terms of CO2. So we have a temperature increase of 0.9 degrees Celsius. Without those sinks, which are a big part are within the ocean, the atmospheric CO2 content would be approximately today 535 ppm of CO2 rather than the 400 we've hit. I always look at Schill, and he will always nod or do that thing if I get ppm wrong. So there's some true authorities here who watch me. So Schill, so far I see you nodding. Anyway, so the key message here is the natural carbon cycle helps us tremendously to take up all this man-made atmospheric CO2 and store it in the ocean. This is a map of the ocean. The global oceanic uptake of anthropogenic CO2 is at the moment 2.2 gigatons of carbon per year. The natural oceanic release of CO2, these are the source areas are in red, the sinks are in blue, is 0.6 gigatons of carbon. So we have a net uptake of 1.6 gigaton carbon per year. And it's just like a water bottle. If you go more polar, your water bottle gets colder, you have a better chance of taking up CO2. But what you see here already here in the North Pacific and the Southern Ocean, this is just about imbalance between a source and a sink, or is already a light source. So something is going on in the ocean which is causing this simple temperature pump a problem. Here's another illustration that's from my colleague in Zurich, Nikki Gruber, a three-dimensional picture of the ocean and a section through the ocean. So this is the Atlantic Ocean. This is 4.5 kilometer water depth. This is the North Atlantic, 60 degrees north. And this is about the way ocean circulation works. You sink, the Gulf Stream comes to the North Atlantic, you sink it to water depths of 3 kilometers about. Then you upwell it in the Southern Ocean, it goes into the circumpolar ring current and is then transported within 2,000 years to the North Pacific. We'll come back to that. And what you see that the anthropogenic CO2 is mainly taken up in the upper part of the ocean. The upper 1,000 meters are mainly responsible of helping us in taking up the CO2. The problem is that the main carbon or CO2 storage is not the surface ocean, it's the deep ocean. In the deep ocean, the CO2 or the inorganic, dissolved inorganic carbon content is about 60 times higher than in the atmosphere. And what's preventing all this CO2 from the deep ocean, the key storage of the CO2 to escape to the atmosphere is that the fact that the ocean is wonderfully stratified. So in the low latitude ocean, we call this a thermocline. You see those caps here on top of that. But you already see that there are some situations, particularly the Southern Ocean and the subarctic North Pacific, where those isolines pretty much reach the surface. And it's the physical exposure of those water masses, which are from the deep ocean, enriched in CO2, and the biological uptake of algal material, which can grow based on this CO2 and bring it back to the ocean. That's what we call the biological pump, which is the key determinant on how efficient the biological pump is and how much the deep ocean can take up in terms of carbon and how much it would release. So what I want to do with you is now, based on a couple of examples from the ocean drilling program, where we look at some cores at the Southern Ocean and the subarctic North Pacific to illustrate in the geological past how these so-called stratification and the efficiency of the biological pump has evolved over the past million years. And so we have these amazing tools, actually two of them. The one is called the G-Cube and then the JOIDES Resolution, which are two wonderful drill ships available to the scientific community, where we now in more than, it's almost 40 years of drilling, have close to a worldwide coverage of ocean sediment cores. It's remarkable technologies. You have enough pipe on board ship that you can drill through a couple of kilometers of water column in the ocean floor and reach penetration depth of a kilometer. So on board of this ship JOIDES Resolution, there's about 10 kilometers of pipe. It's very expensive, but I would say the most successful program in geoneurosciences there has ever been. So what I want to do with you is look at this point first, and then go to this point of Kamchatka to highlight the changes and the impact of the polar oceans in particular on those major climate transitions. And what I want to start with is as a test run going to a colder word from today, which is the wrong analog, but it's still a good test case for certain processes we are behind, which is the glacial interglacial timescale. So we do know there were glaciations. That began about 2.7 million years ago. Then we had the Earth's orbit. The climate is never one-trick pony. There's a couple of mechanisms. So we have the orbital pacing of that and changes in insolation. But we cannot go in and out of ice ages without two major feedbacks. The one is the albedo effect, mainly the ice albedo, but also the land albedo, and then the greenhouse gases. And of course, as a scientific community, we want to understand the processes which drive those changes. The probably single most important measurements the scientific community has produced for recording glacial, interglacial changes and higher resolution climate variations are the measurements on the ice cores. Greenland spans the last 150,000 years. The Antarctic ice cores go back 800,000 years. And it's particularly the Antarctic ice cores which have been instrumental to reconstruct atmospheric CO2 over glacial, interglacial cycles. So these are the last 800,000 years. This is 800,000 years before present. This is today. And this is a temperature measurement in the ice cores based on isotopes in the water of the ice. And then within this ice, the atmosphere is trapped in air bubbles. So what we have here are temperature variations between an interglaciation, warm is always up, towards a glaciation of something like a bit more than 10 degrees Celsius. So this is the current interglacial since 10,000 years. This is the last glacial maximum. And then every 100,000 years we get those glacial interglacial cycles, and then every 40,000 years if you go older. The atmospheric CO2 content is lower, as you would expect in a glaciation, at about 180 to 200 ppm, and in an interglaciation, 280 to 300 ppm. There's just this remarkable correlation between the greenhouse gases and, in this case, Antarctic temperature, but really global climate on a glacial, interglacial timescale. What's also obvious if you look at those greenhouse gas measurements of the last 800,000 years and compare it to the CO2 content of the atmosphere in July 2013 of 397.2 ppm, there's no way that this is anything to do with the natural carbon cycle. And nothing of that magnitude has been observed ever since the Pliocene warm interval. We have to go back really 3 million years ago to have those 400 ppm. And depending on what we do have the potential, based on our giant man-made experiment, to be at 800 ppm or beyond by the end of this century. We'll see later where this would be in an Earth historic perspective. What we want to do, and it's one of the key questions in paleoclimate research, is not just to measure, of course, those variations in CO2, it's to understand the processes which lead to those 100 ppm of glacial, interglacial change. And it's really since the 80s, some wonderful modeling efforts have pointed out that the polar oceans play an important role in that. So what you have here is a map of the salt content of the global ocean. And it's probably the salt content which is the single most important driver. It's salt temperature and the impact on density on the entire ocean circulation. So the fact that the Atlantic has 1 per millimeter salt in the Pacific is leading to the fact that we have a Gulf Stream system which sinks down in the North Atlantic and forms this ocean salinity conveyor belt, that the water particle that sinks down here is going all the way around the globe and comes up as a deep water particle close towards the North Pacific, or at least is reaching the subsurface after 1,000 years. And what you also observe is that the polar oceans have the lowest salinity values, salt values, here in the Southern Ocean, and then the very lowest are here in the subarctic North Pacific. And low salinity leads to low density, and this is what you've seen in the previous picture, the reason that you have something like a very thin freshwater cap, a lid at the polar oceans, which, contrasting the tropical oceans, is leading to quite significant stratification, but debatable and changeable at the polar oceans. So we can measure in the past those changes in the polar oceans. We can measure temperatures, we can measure the ocean's production. And I want to show you one example, just one example out of many sites. This is from the Ocean Drilling Program. So the southernmost site of this transect between Africa and here going through the Southern Ocean, here's the Antarctic continent, is site 1094. And you've seen some of those curves before. These are the upper two, these two curves. This is the atmospheric CO2 content, the last 800,000 years to today again. This is atmospheric CO2, 180 ppm to 280 ppm. This is Antarctic temperature. This is another measurement I don't want to explain in detail, which is a reflection of the global ice volume. So you have here the interglaciations. This is the last ice age, 20,000 years ago, and then every 100,000 years, a glaciation and an interglaciation. Down here is now a sedimentary record, a sediment core. It's a couple of 100 meters long of a sediment core in about 3,000 meter water depths in the Southern Ocean. And this is a very simple measurement. This is color. You just look at sedimentary color. We do many very complicated modeling works and very complicated geochemical measurements. But it's sometimes those very simple measurements which can be useful. So up is a lighter color, and down is a darker color. Lighter colors in a sediment record, which is a mix between biogenic material and then all those glacial material, which is mainly clay minerals and some larger fraction, is a reflection, in this case, of the biological pump. Because lighter colors are a higher deposition, a higher flux rate of so-called biogenic opal. These are diatoms. These are algal plants with a silicate shell. And that's the most important biological constituent of those sediments and the biological pump in the ocean. So what we observe is that whenever CO2 is rising, we go to an interglacial, we get an increase in the biological production. And how do we do that? We have this freshwater lid today, and that freshwater lid in a colder world was stronger, was more severe. So if you have this freshwater cap in a glacial time, which is a more severe physical barrier, you get less nutrients to the euphotic zone and you reduce your algal bloom. If you go to a glacial termination and destratify, right, get rid of your freshwater lid, you expose more nutrients to the euphotic zone, so the production goes up. The problem is that the polar oceans in winter have no light. So you get all those nutrients exposed to the sunlight, but when there is no sunlight, you have no biogenic material to take all the CO2 which is provided to the surface and bring it back to and you can't bring it back to the ocean. So you outgas that fraction from the ocean to the atmosphere. That's called an inefficient biological pump. So it's in the cold climate, it's more efficient than in warm climate. So one important valve for the gas exchange, the CO2 exchange between the deep ocean and the surface ocean are here those polar ocean, as you can think of this as an ocean atmosphere valve. So the colder it is, the stronger the polar ocean is halocline or salinity stratified. We're warming the world. We're not so interested in the last ice age. So the analog we need to look at for our doing is not the last ice age, but if those physical mechanisms and those impacts from the physics of the ocean to the chemistry, nutrients on the ocean to the biology in the ocean, there should be somewhat linear translation. So if we go to a warmer world, we can make the same measurements, and to go to a warmer world, we have to expand the timescale now to this Pliocene warm interval, the reason for our workshop. So the Pliocene warm period is the time between 4.5 million years ago and 3 million years ago. These are the last. This is 5 million years before present. This is today. This is, again, one of those isotope records, a benthic oxygen isotope record, which gives you an indication on global climate. So the higher the number, the heavier those values, the more you go towards an increase of global glaciation. So you see this transition, this very unique transition towards a northern hemisphere glaciation, which starts something like 2.7 million years ago. And here you had an ice-free Pliocene warm period, an ice-free northern hemisphere. This world was 2 to 3 degrees globally warmer and had 400 ppm CO2 in the atmosphere. So one of the questions is what's causing this transition, and the particular question is how do we come from 400 ppm CO2 to then the glacial, interglacial situation with between 3 and 200 ppm. And one important region or two regions to look at are, again, the polar oceans. I want to start with a site location now here off Kamchatka. It's a very old record. It's from really my thesis 20 years ago, but it still works. And we look at pretty much the same in this sedimentary record, which goes now back to 6 million years ago. 6 million years before present is here. This is today. This is a very simple record which shows you at this location of Kamchatka the input of iceberg transported material, and you see there was always a glaciation which wanted to start. It couldn't start. 4.5 million years ago it even went to this Pliocene warm interval, and then it really took off 2.7 million years ago. This is probably the most impressive climatic transition of the entire Earth's history of the last 550 million years ago. There was no northern hemisphere glaciation until then, and then ever since, with at least this rest of Greenland we have today. The record above is now at the same core of Kamchatka in the subarctic North Pacific. Again, one of those algal diatom bloom records. And there's a very remarkable observation we made then, that 2.7 million years ago, exactly in parallel when the world cooled so dramatically, this accumulation of this biogenic material plummeted by a factor of 4 to 5. So this is algal production. It's very high in the Pliocene, and then it dropped down here with the onset of that glaciation. That, of course, required an explanation. The explanation is fairly simple. What dominates the Pacific Ocean and the global ocean circulation today is illustrated here. Here's the Southern Ocean. This is 3-kilometer water depth. So the water comes from the North Atlantic, is going through the Pacific here, and is getting enriched in nutrients and CO2 and has the highest nutrient CO2 concentrations just below the subsurface here in the North Pacific. So this is the equatorial Pacific. This is nitrate. This is 45 micromole of nitrate. And the highest nutrient concentrations are just below what we've seen before, about 100 to 200 meter thin freshwater cap sitting on top of this North Pacific Ocean. This is this halocline. So if we would remove this halocline, it was strong in the glacial, and it probably was non-existent in the Pliocene warm interval or much reduced, we would expose all those nutrients and CO2 to the ocean surface, and we wouldn't have just a spring bloom in May. We could basically continue to have that bloom throughout summer, so it's very easy to get a factor of 4 to 5 and increase in production if the nutrient delivery is going up. The problem is in winter when there's no light, we have a light-limited system, we still physically pump those nutrients to the surface, but can't utilize it. So the unused nutrients and CO2 is outgassing from the ocean to the atmosphere. The problem is we don't see this just in the North Pacific. This is now the same record for the last 4 million years ago, and here we see an additional record now from the Southern Ocean. It's the Southern Ocean record, and we see exactly the same observation of a plummeting biological pump here at the onset of Northern Hemisphere glaciation. And the Southern Ocean, of course, being much larger, probably having a much larger impact on CO2, is playing a huge role in that. And if we compare this to the glacial, interglacial type situation, it's fairly easy to explain with just a change in polar ocean stratification, more than half of a glacial, interglacial CO2 variability, 40, 50, 60 ppm, is in that ballpark. Okay, so these are the different variabilities we have, glacial, interglacial. Here's this Pleistocene transition. The question is, how fast is such a transition? It's a little esoteric to think of something that happened 2.7 billion years ago, but I think the process is highly relevant. So to basically execute this transition, it's only 2 centimeters in a sediment. So if we make higher resolution measurements, the transition lasted probably something like 100 years or less. And that's already getting more relevant to what we are facing. And the question is are the consequences in case we would reverse this, and how easy it would be to reverse this. So with Dan Sigman at Princeton, we asked that question, put it into a relatively simple model, and ask, well, how easy is it to get rid of this halocline type stratification, for example, in the framework of global warming? And the model would just argue that it takes 1 to 3 degree warming. The model doesn't care who's warming, just like the geologic analog, to severely reduce the stratification here in the North Pacific, and it would work in decades to a few centuries. And the consequences would be also just the geological analog, that we would get rid of our Northern Hemisphere glaciation, there would be no ice in Greenland. That would alone lead to 6 to 7 meter sea level rise. A big discussion we have at this conference is the impact on the hydrological cycle, and there's strong evidence that probably the Pliocene warm interval looked like a permanent El Nino. I'm not going to talk about this here, but this is, of course, after the El Nino, La Nina years are the second largest climatic signal after summer, winter. Right? These are huge impacts on the climate system, I think, as we all appreciate. So to conclude that part, in a warm climate scenario, it doesn't matter how we warm the world, there are no or reduced freshwater caps in the polar oceans, and the biopump is having a leakage and can release much of the CO2 from the deep ocean to the atmosphere. And in a cold climate scenario, we've stratified, the biopump works more efficient as we have this freshwater cap sitting on top of that part of the ocean. Okay, that's a 2 to 3 degree warmer world. To get the full perspective of this potential by the end of century 6 degrees Celsius, we have to go which is something frustrating further back in Earth's history. So this is one of those global climate curves compiled by Jim Zachos from Santa Cruz, and these are now the last 70 million years. So what he has here is somewhat a temperature scale, plus 6 degrees and minus 3 degrees Celsius, if we take the glaciation, inner glaciations into account, and then go to the so-called Eocene warm interval, a warm time about 50 million years ago, until when the world was at its warmest, and it was a totally ice-free world. So the Antarctic glaciation started something like 35 million years ago. Northern Hemisphere glaciation really intensified 2.7 million years ago, and this was a totally ice-free planet. The CO2 reconstructions are rough in the older part of the Earth's history, but probably the Eocene warm interval was something like a 2000 ppm world, and then we went down to 1000 ppm in the framework of this cooling trend. This is the Pliocene warm interval, we just looked at 420 ppm, and this is the glacial, interglacial type range. The anthropogenic CO2 peak would bring us unhappily to probably 1800 ppm, which the Earth hasn't seen during the last 50 million years ago, and which of course would be a totally ice-free planet. If we burn all those 5,000 gigatons, we could probably fairly easily access. And then if you get a little cynical, but I think it's important for those skeptics, hopefully not in the room, who say, well, you geologists argue it all happened before, and it's the scales, right? Those time scales. So if we look at the IPCC report, right, 6 degrees Celsius warmer in Earth history would require 50 million years, right? So the 9 gigatons we burn took basically with the natural carbon cycle close to 1 million years. What we do per year takes the natural carbon cycle close to 1 million years to remove it from the atmosphere. So the scales are totally changing, which shows you how dramatic this experiment, depending on what we are doing, could potentially be. Why do we care? So let's switch to the youngest Earth history and not look at the impact of us on the climate system, but let's take 2 examples, and I'm trying to be quick, and look at the decadal timescale and look on how past societies have been impacted by changes. And what I want to focus on are the tropics now. What we see is now an animation starting January of the annual hydrological cycle. This is precipitation, and we're going to look at two site locations. Cariaco Basin of the Venezuelan coast. This is cute little basin, which is one of the perfect archives of laminated nature of sediments, where we can really look at annual varves, and then some lake sediments here in China help us do similar. So what you see going on from January, February, is that the ITCC, the tropical rain belt, is moving north, May, June, July, bringing rain to Yucatan, and then the summer monsoon, and then over the course of the year moving south again, and is redistributing the rainfall in winter to the southern hemisphere. This is reflected in this Cariaco Basin, these beautifully laminated sediments, and we've learned to read those sediments with geochemical measurements, with sedimentological methods. I'm not going to go into details, but what we see in dark laminae is that elements like iron or titanium are enriched. And they're mainly enriched because there's an increase in clay minerals when it rains, and rivers bring those rainfall to the basin. So what the Cariaco Basin has been beautifully suited to, if you look at the titanium content of the last 14,000 years, is to get a tropical rainfall curve. So here's the last ice age, which is very dry, and this is the younger Dryas cold interval, 12,000 years ago, and then you go wetter. If you go to the Holocene thermal maximum, and then you have this drying trend over the Holocene. And then you see those wiggles, this is probably the onset of a modern ENSO-type system at 4,000 years ago, and this is what we call the Little Ice Age. It's very tempting to use those records and increase the resolution, and then combine this with a cute society, a very important society, the Mayan society, which lived in that part of the world. So these are the last 2,000 years ago. Low is dry, so this is the Little Ice Age. When it gets colder in the northern hemisphere, the ITCC, the rain belt, moves south, so that location is getting this triple peak of the Little Ice Age. And then the Mayan society did really well there on Yucatan. It's exactly the same climate swing. until they collapsed in the 8800s. So we produced these records, published them in 2003, and used some then novel XRF scanners. And when you talk to archaeologists, we could do a measurement every 2 millimeters. We're really, really proud of that, a measurement every 4 to 5 years. I was told, well, young man, you got to do better. If we don't do annual, it doesn't work for us. So new methods came up, laser ablation, ICP-MS, and much is analytic driven, or micro-XRF, and then we did over a slab of 30 centimeters, we put a couple of thousand measurements, got still the same dip here in the 8800s, and found on really an annual or many measurements per year that during the classic Mayan period it was wetter than in the collapse phase, which was drier. This is a heavily smoothed record, and what we were able to do, if we look at the details and then compare this to just some beautiful results from our colleagues in archaeology, is that we found what they've described as an abandonment of the Mayan cities, last inscription of the stele, and very sophisticated archaeological work, that we find the same three phases of collapse between 760, 810, 860, 811 and 860, and 861 and 910 to be multi-year pulses of extreme drought in that region. I'm not a climate determinist, but what we keep finding with these and many, many other records, if we can provide the appropriate resolution, that particularly in the tropics, the hydrological cycle, at a society which was really at the edge of the carrying capacity of their environment, became very vulnerable to environmental change. And the Mayans clearly showed those signs, with all other impacts as disease and warfare, to respond to this. If we go across the Pacific, and you remember this movie, the same shift should be important for the Asian monsoon system. So there's a lake, Lake Huguangmar, which is also a very fine climate archive. I'm not going to go through all those measurements we've done over the last 16,000 years. I'm just going to focus also on the same time interval initially as we've seen before. So this was 1400 to 1,000 years before present. This was this triple structure which led to the collapse of the Mayan society. And you see this record above. This is not the parallel core in the Cariaco Basin. This is really all across the Pacific. And if we get the x-axis, the stratigraphy, the timescale right, this is Lake Huguangmar in China. And it's just a remarkable coincidence that those large swings which led to the demise of the Mayans, which also, interestingly, when compared to Chinese history, had a huge impact. So it's always fun to have those measurements, and then, particularly on a vacation at the beach, take a nice textbook on Chinese history and compare this with your wiggly lines. It's really a fascinating thing to do. So I've done so with this cultural atlas of China. I know nothing about Chinese history. But what I've learned that the historians in China raved about the Tang Dynasty, one of the most important times in Chinese history with all the inventions, etc. And the peak of the Tang Dynasty ended at around 1250. This is just when the peak of the classic Maya period ended. And then the Tang Dynasty, just as much as Chinese history, went through those phases of peasants' uprising, famine, and huge problems. And then at 907, within the same 3 years, at 910, the Mayas collapsed. The Tang Dynasty collapsed. Still not a climate determinist, but it's very suggestive that those two societies, very important societies on both sides of the Pacific, which just respond to the same swing of the ITCC in the monsoon system, would basically respond so strongly to those huge decadal scale swings. We've then taken that a step further, and that we should have not done it. I was really in trouble with many Chinese scholars. I felt, because I learned that as a European to make a point, and Abby is excusing me on the Tang Dynasty, is like probably someone from China trying to make a point on the French Revolution. That's not going down all that well. But anyway, if we take that plot to the entire 4,500 years of Chinese history, you do find with those wet, dry swings that all dynastic transitions happened during times where the monsoonal rainfall was unfavorable. You also learn that there are many big swings when nothing happened, and this, I think, is where political leadership is playing a very important role. So my first conclusion is, I think it's the rate of climate change, which is just as important as mean climate for those socio-political impacts, as rapid climate change may be more easily led to disconnects between social policies and environmental realities. And if you look at those curves, I think it's remarkable how little we've learned. So what are we doing? What can we do? And what are we doing? So what we're doing is, again, coming back to the beginning of the talk, this is global CO2 emissions and the global population. I found this here on the internet from the US Census Bureau. And what we see is probably what we expect, that the global population now rose to 7 billion and the CO2 emissions just go in line. We see that with the very rapid development of some parts of the world, the CO2 curve is steepening. So if we just stay basically on the trend, and at the moment we're doing it and probably even steepening, we're just going to skip our Pliocene warm interval and probably go right to the Eocene warm time. So there's something we got to figure out, that this curve is going to turn around and we're going to stabilize this atmosphere. Otherwise, I think we're going to have a real crisis. This is, again, the picture I mean. At the moment, we're just going up here and we need to go down there. So we really have to reduce the emissions, I think, at least by 50% by 2050, if not more. Could we do that? I'm not an expert in that. I always liked a pretty old study from Princeton University, Pakula and Sokolov, 10 years ago, had this concept on wedges. So each of these wedges can reduce the CO2 emissions by 25 gigatons in the next 40 years. This is probably not going to be good enough, but it would be something. And each wedge is basically one of those technologies: energy efficiency, the energy shift, particularly, I think, to renewables, CO2 capture and sequestration. So there's not one solution. I think there are many combined solutions. So we could basically, if we would make those investments with today's technology, reduce 15 wedges, which is about 400 gigatons, to stabilize probably the atmosphere at around 500 ppm CO2. The energy is there. This is a very interesting study which was made for the German government and Greenpeace. Solar, the sun has 3.8 times the energy we would need. Geothermal heat is playing an important role, and so on. So I think there is the potential to do it. It's expensive, but ultimately it's much cheaper to do that than not to do that. So in the business as usual scenario, we still are energy hungry. All growth is based on energy, and the total costs of $11.3 trillion plus the fuel costs until 2030, as gas, coal, oil costs something, is 15.9 trillion based on this study. The renewable energy scenario would take high investments initially, but the total costs actually would be higher, but then the energy costs would be much cheaper. So I think much could be done. At the moment we're doing not very much, and I would like to conclude with the following slide. We are clearly in the midst of a global warming, despite the popular press sometimes having other opinions. The anthropogenic greenhouse gases are the main cause. The natural carbon cycle helps us at the moment, but it's clearly not the solution. Global warming by 2100 of 7 degrees Celsius is possible. It would be an absolute disaster. And there we have risk for surprises like those thresholds we've experienced going into Northern Hemisphere glaciation. If we reverse the natural carbon cycle into not helping us, but outgassing all the CO2 from the deep ocean to the atmosphere, would be a good view. And then something, this IPCC people, and somewhere is Betty as a very instrumental person, are those climate freaks who make those crazy scenarios. I think if we look at the paleoclimate data, and all the corrections we have to make from IPCC 4 to this month's IPCC 5 have been corrections upward, meaning in terms of bad news, that the IPCC was rather too conservative and, if at all, underestimates some of those thresholds and feedbacks which the climate system, the ocean atmosphere system, has for us. Thanks for your attention.